Okay, well, thank you very much to the organizers. This has been a fantastic meeting. I'm enjoying it immensely. Um, and I'm going to talk about a line of development that involves a part of physics that's very solid and easy to analyze by humans, that allows us to make what I'll call formulaic improvements in optimization sampling. And so I'll try to lay this out. And first, let me highlight the wonderful collaborators, starting with Bruno De Luca, who's a postdoc in my group, and Alicia Gate. And then on the sampling side, Urs Seljak and Jakub Robnik, and also Henry Zhang, who's a student of Leonardo Senatore, is joining in. Also, thanks to Dan Roberts for getting us into this via the kind of connection to inflation that we heard about in Sven's talk, and Dan Kunin for really useful advice in some of our more recent analysis. So that's going to be the main theme. And then if we get there for fun at the end of the day, I'll say some things about more general things about AI that come to mind, attempting to replace myself. Oops, sorry. No, I know what I need. Okay, so the outline is that basically I'll introduce this general framework, and I realize some people have heard a version of this talk before. There is news in it, so I want to get that across. Sorry, excuse this targeted ad for Jesse, but it just popped up. And for those who know what this is, I'll explain it later. And so we'll go from general framework theory and experiments and benchmarks before trying to replace ourselves. Of course, there's a nice talk toward the beginning of the week that says that anything about optimization is already such that machines have replaced us. This is really complementary to that because it's in both cases, it's all about the hyperparameters. In one case that we heard about, with enough resources, you could do a brilliant job of tuning those, making a huge space of them and tuning them to improve optimization. What we're going to do is use our understanding of Hamiltonian dynamics to understand how they relate to each other and what their natural values should be, leading us toward tuning free versions of these algorithms that we can understand in that manner. And I think it seems to me that the right answer is some kind of collaboration between these two types of approaches, and we do have good results so far. With more to come, in particular in optimization, our experiments are behind our theory, and we need to get them up to speed. Okay, so that's where we're going. Okay, so these are the two tasks. Everybody here knows that there are these tasks and that they play a role in science, including machine learning. So Hamiltonian dynamics is our theory of particle dynamics that applies very widely. It's generically chaotic. It's generically, it's a theory that extends to high dimensions very easily. And what we're going to do is use it to engineer new optimization and sampling algorithms with good properties. Okay, so let me compare to the traditional gradient-based methods. So on the left, on optimization side, that is gradient descent with momentum, and its many, many relatives, in particular atom. And of course, it works very well. It's part of why this is a revolution already. In physics language, what that is it's particle motion on some potential energy landscape, the loss landscape, with friction playing a key role. So this going from physics to ML, in this talk, I get to say F equals MA. So we start from that basic formula in physics, recognizing that in gradient descent, friction is part of the force. And that's how one thinks about this in physics language. What that means, though, is that in physics language still, the energy isn't conserved. And in this context, with the kind of vanilla Newtonian dynamics, the friction is essential for getting it to converge. So you might think that's how it must be. But as we'll see instead, you can pick a Hamiltonian that very understandably allows convergence, generates convergence without any friction, so consistently with energy conservation. And there are consequences of that, which gives us these formulas that I'm going to highlight. Okay, on the sampling side, the comparison to make is with Hamiltonian Monte Carlo, which has been mentioned a number of times also here, so it's a gradient-based approach to sampling. It involves propagation along iso energy surfaces, but then resampling momenta according to a Gaussian distribution, which means drawing new values of the magnitude of the momentum. And as was mentioned in at least one talk, one aspect of that is that it's then exponentially hard to kind of go between modes because you're trying to draw a huge momentum to get over some barrier. In any case, that's the thing we should compare to. And in comparison to that, we'll see that instead you can have dynamics just on straight up, just on a fixed energy surface, taking again a Hamiltonian such that when you marginalize over the momenta, the measure on the target parameter space is the target distribution, period, with no need to resample the magnitude of the momentum. Okay, so those are the ideas that go into this. So in this crowd, happily, we don't have to introduce Hamiltonian dynamics, but here it is just for completeness. And let's start from the phase space volume, which is conserved in Hamiltonian dynamics, and we'll make great use, a lot of use of that. So we integrate over positions and momenta with a delta function for energy conservation. And assuming it's chaotic, and we'll talk more about that, then this measure formula applies, and the probability to find a particle, say, if you do multiple droplet of multiple trajectories, after the mixing time defining the chaos, then the probability to find a particle from some droplet is proportional to the phase space measure. And so the whole idea is to take a Hamiltonian such that that phase space measure is what you want. So for optimization, you want it super concentrated toward the bottom of the loss. For sampling, you want it to be exactly your target distribution. Okay, so that's the plan. And through all of this, the hyperparameters enter, and we'll use the energy conservation relations to understand them as much as we can. Okay, so that was sort of abstract. Two examples are, instead of doing ordinary Newtonian mechanics, do relativistic motion. Then whatever the relativistic speed limit is, you can't go faster than that. So if you make that die as you go to the bottom of the loss, well, then that's why you converge. You can't go faster than that speed limit. That's kind of the most fun example. A more vanilla example, which we end up working with because it's separable, is instead to take a variable mass. So do take sort of Newtonian dynamics, except take the mass to vary with where you are on the loss landscape. Make it in particular a function v of the loss f, or of the target density in the case of sampling. Okay, so in this case, when the particle is light, it goes very fast. When the particle is heavy, it goes very slowly, and that's how it converges here. Very, very clear. So, and in particular, in both of these, you see why you do not need friction to converge. So you can have energy conservation and still converge. And then you can ask, okay, well, what does the energy conservation buy you? And one thing I've already highlighted is that it buys you this measure formula, whose virtues I already extolled. The other thing that we'll keep better track of than we did actually in the initial work, kind of stupidly, is to keep track of the other thing it buys you. I mean, it also buys you, if you express the Hamiltonian as a function of the loss and parameters and the velocity, then of course it gives you a function for the speed that it's moving over parameter space. So we work with both of these formulas to get a question already, please.
So wait a mic because we're recording and yeah.
Thanks, sorry. One of the really nice things about Hamiltonian dynamics is that we have integrators for them that are like exactly reversible and like symplectic. Like, can you still do that when you make the momentum like position dependent?
When you make the mass position dependent, yes. So there's a separable Hamiltonian that I flashed a moment ago, and that's one of the reasons that we went to that. So this one that I wrote, I've written it here in kind of the physics intuitive way, but if you just take a log of it, then you get something separable and you can use all the fancy integrators. So that was actually the reason that we went to that case, was those weeds, as you call them, but I guess it is well known that makes a difference. So Does that answer your question?
Yeah, that's really cool. I didn't know you could do that.
Yeah, thanks. I'd love to discuss more because again, if you've just made us humans obsolete, that's just great. That's fine. But my hope is to collaborate still for a while before I should retire. I'm sorry. Actually, I'm of an age where I should be working on longevity research, but never mind. Sorry. Okay, so we're going to use these two formulas in concert. We're going to focus on hyperparameters and the dependence on dimensionality. And we'll see dimensionality is actually, we overcome the curse of dimensionality in a certain way. So we'll call it the charm of dimensionality. And if we're careful about our use of these formulas, we can also make progress on hyperparameter tuning. Okay, so what are the hyperparameters for us? Well, we have a learning rate. We're going to introduce in this V of F that I variable mass, the function of loss, or at least some parameter eta is there. There's this loss offset for Jesse.
Sorry. Eva, excuse me, it seems your mic is not working. Maybe you can just take mine a while.
Sorry. Okay. No, now I feel like I should do more comic stuff. But anyway, so okay. At first, it seems like we have a kind of an alarming amount of hyperparameters. One thing we don't have though is a momentum hyperparameter in the sense of SGD, and we don't have the epsilons of atom, whatever. But what we'll find is that there's a very clear thing to do with F naught. That eta we have a systematic improvement as we increase it. That with some parameter to do with the chaotic dynamics, we know how to fix that in terms of the dimensionality of the problem. And the learning rate is also understandable that that's kind of still in progress. Okay, so chaos. So I introduced this formula for the measure based on chaotic Hamiltonian dynamics. And, we physicists all know that that is kind of the generic case. You have to explain yourself if you have a system without chaos, that usually requires extra symmetries and so on. And yet actually in these problems, we found that we really did need, both in the optimization and the sampling case, to introduce some elements that are consistent with the energy conservation, but which encourage chaos. And there we took some inspiration from mathematicians who have proved rigorously the certain mixing properties, ergodicity being the weakest, but sort of stronger mixing properties in billiards problems. And it's clear, sort of inspired by that one can introduce bounces. So basically things analogous to bounces off a billiard ball, whereas you can see you do have sensitive dependence on initial conditions as the trajectories hit the billiard ball, say they come parallel, they bounce off with a diverging trajectory. And that's basically why they're chaotic. We can do that consistently with energy conservation. So basically, long story short, we introduce that. In the most recent stuff, driven by the sampling paper led by Jakub Robnik, we do that in a kind of piecewise way. So there's this one parameter nu that says how much do you do a momentum reorientation at fixed magnitude at every step. The angle of that is related to the dimensionality n. In this formula, alpha is nu root n. And basically the upshot is there's a typical set on which you propagate, and you want to bounce per orbit of the typical set. So you can fix that parameter in a tuning-free version of the algorithm. Okay, so you do need chaos. Maybe I won't belabor that for a short talk. I was a little surprised by this because of the physics intuition that things are generically chaotic, but it is true that this chaotic inducing element helps, and we see that both in the sampling and the optimization. So a system can get stuck in a periodic orbit, but adding these simple features kicks it out of that, and you see it in the experimentation. Okay, I already said what some explicit realizations are. Let's introduce it. Okay, so the thing about this that's new is this direct dependence on the loss, which means, say, for some problems you have a nominal knowledge of the zero of the loss, which might be at zero. Even so, if you don't have enough data, you might not reach that. And in general, you don't know what it is. So we put a parameter in this F naught, which starts out life as kind of a fudge factor for that, an extra hyperparameter. But let's see what we can do with that. So the dumbest thing you can do, say for often machine learning problems where you have some loss whose goal is essentially 0, you can just set it to 0 and you get reasonable results. So we get, competitive with Atom and better than SGD by doing just that, which is kind of why we're slow to do anything more sophisticated. There is an adaptive way to tune it, which is in our code, where if you overestimate it, you can discover that through the discrete jumps and kind of readjust it. But the thing I want to present here is using our energy conservation physics formulas to figure out a better thing to do with F naught, and that's kind of where we're going. Okay, this is the adaptive tuning. Just you can see it. Okay, as we heard earlier in the week, you have to have a theorem. You don't want it to be your joke. This is the theorem. It's that you simply can't, except for in set of measure 0 circumstances that don't happen in practice, you cannot get stuck in a local minimum. You just can't, because that would violate energy conservation. So it's not a joke. It is a very simple theorem. It's not impressive in some mathematical sense, but we like that in physics when things are simple to explain. So that is a feature of the energy conservation. Okay, so now let me come to the sampling side of things, where the goal is to sample some P of theta. Let's write it as e to the minus f of theta, it doesn't matter. And then take this idea of doing that by choosing a suitable Hamiltonian, such that when we integrate over the momenta in this general formula, that we get a distribution in parameter space or position space in physics language that is the target we want. Okay, so in this context, what that requires is taking V of f in the variable mass formula to be specifically e to the 2f over n, where n is the dimensionality. I apologize, I'm using d and n both for the dimensionality in some formulas here that I realized late. Okay, so as I sort of already said, when you do sampling, it's well known. I mean, so in sampling or just propagation on these kinds of target spaces, right? You have, suppose you're kind of looking around some basin. You have the geometric measure in theta space, so d theta, theta to the n minus 1. That by itself pushes you out. Your target, say it's a Gaussian like this one I've written here, at least approximately near some peak, some mode. Combining those two gives you a saddle point. That's called the typical set, and it scales with the square root of n, the square root of the dimensionality. And so we know what that is. And this thing about the chaos hyperparameter says we do 1 full bounce per orbit of that. And then we're good. And that turns out to be correct. Okay, so to check how this approach works compared to the canonical, we'll just call the usual HMC canonical, and ours we call microcanonical HMC, so MCHMC, the first MC being about the energy conservation, microcanonical. So the kind of artist's rendition of the differences is over here. As has been said before, we have various measures of how well it's doing to generate samples of the target distribution. We'll do various benchmarks of that. You want it to be, at least some high point functions, nothing trivial. So, here are some that we used in our first paper on this. The effective sample size is measuring how many evaluations you need to get this correlator to be nearly, this B2 to be 0.1 to get as close as that to the truth. What you need to know is higher ESS is better when I go toward the experiments. Okay, so we do various of these experiments, benchmarking it. I won't dwell on this. These are, I'm new to this whole thing, but these are evidently standard benchmarks one can employ, and it comes out well. So we use the sort of most sophisticated version of HMC. There's something called NUTS that enters to that. We even let it not count its kind of burn-in phase and so on. And MCHMC comes out better. Now, one thing that's interesting about it is that it comes out better in a way that improves with dimensionality, and there's some intuition for that. But it's a true fact you can just see in the results. One difference between the two is basically HMC is going fast near the mode, near where you're trying to sample a lot, whereas the point of this energy conserving stuff is that it's going slowly there, and so it's less sensitive to the step size, and that's kind of a limiting factor of HMC that screws it up at higher dimensions, which doesn't apply here. So these are some recent works, well, in the same kind of general area that Ben and Gary's beautiful talks kind of introduced, not discovering some new discovery here, but it's a neat, more real world benchmark of this method, and both Urush and collaborators and some totally independent group reproduced that it's coming out better than HMC. So that's the status. Any questions about anytime, you just raise your hand. Yeah, Ben.
How do you set the energy, since energy is conserved, you set it and you forget it, but how do you set it?
Yeah, as you say, it doesn't really matter here. So yeah, there's a more nuanced answer to that in optimization that we're coming to that we maybe can talk offline about. So let me just say, if we do take for the reasons that were asked about earlier, if we do take well, also I should say this paper had a version of this already, just not the chaos. Yeah, you can see it completely goes away in this formula. So the original energy and the variable mass is indeed just a additive factor there. So
how well you do with something?
So yeah, maybe I don't. Yeah, I don't have any insight into that. What does matter, right, is that you continue to conserve energy to a good approximation, right? So it's more. Does it help? Does it? Yeah, no, that's a good question. Probably Jakob, who did these experiments, could answer better than I'm answering right now. Sorry. But as you say, conceptually, it shouldn't matter. I think, yeah, as I understand it, the big difference is this thing about where it's going fast versus slow, because this one, again, is going slowly near the modes, whereas HMC would be going faster, right, because the potential is low and its kinetic energy is dominating. So that's a very big, clear difference. Sorry, I should have a better answer, but I don't know off the top of my head. Thanks.
Quick question about earlier part when you have the theorem.
I was
wondering if you can refine the theorem to quantify how much time it spends around the neighborhood of the local minimum before it gets, and compare it with other forecasts.
Yeah. So there's an interesting question. Of course, in ML optimization, there are going to be mini batches. We do it with that in place and so on. And what the statistics of that at late times are is interesting. There've been studies of that, to death in SGD. There's kind of a generalized Brownian motion that happens, and like Shou wrote these papers carefully doing the discrete version. So we've thought about that a little bit here. It's quite different. It's a nonlinear Hamiltonian. But I think one of the things that happens is with regard to Brownian motion, you can ask, what is the expectation value of theta dot squared of V squared? And here it's just forced to be small based on, the energy conservation. So because of that, it's less volatile, I think, than SGD is. But it's on the to-do list to do a kind of fluctuation dissipation analysis of this. So it's a very nice question. Yeah. Okay.
Yeah, I have actually a follow-up question. Yeah, since it's so since this energy conserving algorithm moves slower in higher density modes, it has much better sampling quality. But when you have a several modes, basically, it should struggle between moving between modes, right?
Well, actually, I think there still are issues with multimodal. We have some that's, somewhat separate, but still kind of close to the typical set. But really, so in HMC, and this was said in one of the earlier talks, right? In order to go between modes, you have to draw a huge momentum to get over the barrier, right? And that's why, as was said, it's exponentially suppressed to do that. Here, you do not have to, there's none of that, right? You just on the same energy surface, you can easily go across, right? What you're highlighting is, yeah, but you're kind of taking lots of samples at one mode, and so in order to get there, you have to stop doing that, right? But that's one place where these bounces come in. And the way I like to think about it is there's that which can kick it out of where it's orbiting locally. Also, just by the way, these Hamiltonians because they go fast away from the modes, they get to sort of infinity in the natural metric of the position space in finite time. So one can put in a boundary condition that also helps with chaos, like one of these. Yeah, there's a name associated with that in chaos theory, and that kind of. So going to a very far away mode is kind of like going just somewhere away from the original mode, and that could include getting to the boundary, whatever, but it does get to the boundary in finite time. So that's why there's more hope here that it doesn't just fly away to, forever. It could, again, it takes a finite time to get to the boundary, so you can well explore and find the other mode. But it's still, because of step size issues and so on, it could still be hard to find the other mode if it's arbitrarily separated and arbitrarily small, right? There's no free lunch, but the issues with this are very, very different than Hamiltonian Monte Carlo for these super clear reasons. So yeah, thank you very much for the questions.
Questions?
Okay. Okay, so I was happy to see, these folks kind of back react this onto cosmology again. Okay, so now let me come to optimization. We use the same idea, but now what we're trying to do is we really don't care how it gets somewhere as long as it's fast. We just care that it gets to a very good low-lying region of the loss. So here's where we can have the charm of dimensionality. So I've again written this thing with the obvious geometric theta to the n-1 factor. If we look near, we've gone to somewhat low in the landscape, which happens quite quickly, and look at the measure formula, it has that theta to the n-1 times 1 over v, v being this inverse mass or the squared speed limit, to the n over 2, where n is, again, the dimensionality in this formula. So if you do sort of the naive thing and you just make v be the loss, we'll include f naught shortly, but anyway, if you make it just be the loss, then you overcome the curse of dimensionality logarithmically just already with that vanilla choice. But this is where this parameter eta that I advertise will come in. Instead, we can do some super simple-minded thing and just instead take v of f to be f to the eta. And now the thing downstairs is some power that makes it overcome this, even much more strongly, just arbitrarily strongly according to this formula. So we can use that parameter eta to accentuate the results toward the bottom of the loss. Now, let's include everything here. And as I said, bring in the formula for the measure, but also the formula for the speed. So in general, we don't know the value at the bottom. So we have this f naught. We can still expand around some low-lying quadratic minimum. That's a generic thing that happens wherever the bottom is. And look at our measure formula. Take the saddle point value of theta in that system. So that's here, this theta star. Express it in terms of the hyperparameters, including eta. So there's some clean formula for that. At high dimensionality, this goes down with eta at fixed f naught. But also keep track of the speed of propagation. And in terms of these same parameters, that's written here. And what you see is actually, if you take f naught to be 0 and F min is too small, then actually at high eta, even though the measure is concentrated at the bottom, in fact, you're slowing things down way too much, and you just never get there for that reason. That's a little bit like your question over in sampling. But once you write these equations, the solution is obvious, which is to take this F naught and turn it on, make it at least minus F naught at least as big as 1. Okay, so this is a very simple thing. You do that, and that gives you still the benefit of accentuating the loss at small values while maintaining speed. Okay, so that is a theoretical consequence of the energy conservation. So I just restated that here more simply. And we do a lot of testing of these consequences of energy conservation. So we can do experiments benchmarking the thing, but also first checking if it all makes sense, if it all fits with the theory of these things I keep stressing. The formula for the typical value of theta star and its time derivative, as well as yeah, so that's basically the measure formula and the speed. So when you check experimentally that the trajectories end up obeying those predicted relations, it works, it's true, as it should be. And okay, but this is where our experiments are a bit behind our theory, because this was a kind of belated realization that we should take F naught that way. What I've shown here is this current state of the art if we just do the dumb thing of setting F naught to 0, where if we do some summary statistic of a bunch of different small, medium-ish, but basically small, but diverse benchmark problems, we find that this ECD with F naught equals 0 is statistically significantly better than SGD, but not statistically significantly better than Atom. And there are places where it shines, like these kind of image things, it comes out very nicely. Others where Atom wins, and we're very eager to employ our most up-to-date theory, in particular this thing about the hyperparameters and F naught, to improve upon this. And with that theory, I just want, on the face of it, once we do this thing with F naught, it predicts that with eta we can systematically improve it. And so we really should be able to generate a gap with Atom. But for F naught equals 0 instead, that's the current status. Okay, I am a bit into the weeds of this, but I hope it's clear enough. And it's a very different framework. So the fact that it's competitive with Atom and these friction-based things are very different, sort of like in the inflation context that Gary reviewed. We have slow roll inflation, and then we have other things like Born-Infeld, which give very different signatures. There's very different dynamics. So, they should work differently, and we're still in the business of pulling that out in full here in the optimization side. Yeah. Yeah, please.
Why it would be better like CFAR versus,
I don't know. Yeah, that's a great question. This is actually a problem on which this is where Daniel helped us out, and it's where we're getting the biggest advantage. There's some tricks people use on these problems, like stochastic weight averaging. And so when we use those things, this is saying it's a better sampler than SGD is. That's sort of the intuition.
yeah.
But I think there's more to say about that. Oh, the other thing I should say is, even though we haven't done the full statistics on this business that I'm stressing in the weeds about our hyperparameter relations and how we should really do it most optimally, when we do that and we play around with it, we land on results that are really indeed much better than Atom, as I'm saying they should be. I don't want to advertise that as a complete study yet, because we should do full statistics on that, but the theory, again, it is formulas, and it is making that prediction, and we're starting to see it experimentally. And then once we do all that, we can revisit the question of how, does it have any particular advantages or disadvantages on different problems.
Yeah.
Maybe you have a better idea, but that's okay. Yeah, so here's the tiny ImageNet thing, where we first of all check that we do have in the training loss the monotonic improvement with eta that we're supposed to, and it happens, and this happens across the board. You know, I can just kind of flash through the other benchmarks, most of the ones I kind of put in the tables, and these other synthetic ones where you again check the measure formula. You find actually an advantage on shallow valleys as well that you can derive by hand also, and sort of on very different, kind of related to the previous question. If you have these shallow values, that's one kind of thing people like to imagine for over-parameterized networks. In other problems, you might really have highly non-convex functions, and it you know, this not getting stuck thing is helpful there. So you know, there's a litany of benchmarks that whose summary is what I tried to already show you. Okay, so this is the sort of summary. Gary already asked about the noise and so on. That's what I had to say about it. You could ask about representation learning and how does this affect that. And let me just quickly say that even if you're not going to representation learn, the bounces will generically push, you know, bounce you into all the directions. So you would at least representation learn in that sense. And that's kind of a fun fact about the chaotic dynamics. You can also use it to and benchmark it on PDEs where it finds multiple solutions that we set up to be there. So as far as this part, you know, that I've already sort of said, the summary, before I get into the lighter side of things that I promise if there's time. Are there any more questions on this, or did you want to see more of the details of those benchmarks?
Just maybe because I missed it. So when you, I think I understand the sampling part, but when you're doing it, using it to optimize, why does it stop?
Yeah, perfect. So, okay, so let me go back. No, it's fine. It's good. I'm glad you're asking. Unlike your previous question, I think I can answer this one. So, here are like the two canonical things. In the case of BI, stops because it can't go faster because of the relativistic speed limit. In the case of the variable mass, it's set up so the mass is inverse to the loss, or this loss to the power. And so because the particle is getting super heavy, that's why it stops. And the point about it. Okay. So this is the parameter F naught that I've been going on and on about. So the more nuanced things. Okay. So again, okay. So here's F naught. That's what you're asking about. And there are three ways to address that, each of which has worked in different contexts. First of all, if you set it to 0, you get quite good results. It's coming out as good as Atom if you just set it to 0 in situations where you're in these kinds of benchmarks I was talking about. Now that's not a totally satisfying answer, but it's an experimental fact.
Then you just stop the optimization.
Yeah, that's right. These things never get literally to 0, but it is slowing down quite a bit, and so that's why it converges. You know, similarly to Atom, but there are better answers. And that's what I've been going on about in something like chemistry, which we've also been playing with. You know, it's like EV scales, but you don't know value, and that's where this adaptive thing really works nicely. But as I keep saying, later we have theoretical calculations making better use of both of these consequences of energy conservation. So, yeah. So we have these two consequences of energy conservation: the formula for the speed, and the formula for the measure. And what you're getting at is, you know, if this again, the speed could just, even though officially the measure is greater at the bottom, if it slows down too much first, that's bad. And indeed, the better thing to do is to look at the saddle point, which is kind of the analog of the typical set of sampling, but in this problem, and see that the saddle point value of theta star still can be parametrically driven down by choosing the Hamiltonian, choosing this parameter eta bigger and bigger, provided that you choose this parameter f naught such that you don't let the speed die. And so that's the kind of way we address this. And I've said it before, but with optimization, we kind of belatedly realized even though these are kind of simple theoretical points, we realized it sort of belatedly. So our experiments haven't yet, we've anecdotally seen that very much happen, but we're still in the business of benchmarking using that. So that's basically why it is that. So when I come to the conclusions, I would say, MCHMC, or there's a Langevin-ish version that Urash also worked out with Jakob, that according to what we've seen, it seems to be better than HMC, so people could use it as it is, and that seems like a good idea. For the ECD, I'm very confident we can generate more of a gap, and we're in progress with that. So that's in that sense a little bit behind, but
yeah. So can you say a little bit on how this differs between cases with low number of parameters versus high number of parameters? Is there some?
Yeah, so well, it's we do like, if you like, you can just do like simple low dimensional problems, and it works very well. But I do think the nice thing is this charm of dimensionality business, where if you are near some minimum, and this F naught isn't huge anyway, so basically it's this formula, even though the dimensionality would push you way out, the other factor pushes you back, and it overcomes that in a clear way. So this is well suited to do better and better at to deal with the dimensionality at higher and higher dimensions. And observationally, or whatever, experimentally, we see for MCHMC versus HMC, HMC degrades as you go up in dimension in a way that MCHMC or MCLMC, sorry, another acronym, in a way that it doesn't degrade. So that's when you do this is great all gradient based, so you need the gradient, but anyway. Okay, I guess we're out of time. Let me just finish with my joke, which is a true story. So well, I have these ways of trying to replace myself, including as a quantum field theory professor, networking GPT-4s to get it to do better, and then also getting it to discover some ideas that we had in physics. So we had some really beautiful talks this morning by Magdalena, for example, about geometry. There's another way to do that, which is, these other geometries that are more curved. So let's suppose we look at hyperbolic geometry and we ask for help. So, well, it turns out, don't bother asking lambda for help, because this is what Bruno found when he did that. I don't know if you can read it, but it says, I'd be happy to help with your question about M theory compactified on a finite volume hyperbolic manifold. However, before we dive into that physics, I want to clarify that the term hyperbolic can sometimes have negative connotation, and it just refuses. It just really, we couldn't. We could not get, this is a chatbot version of Lambda. I totally respect that it's open source and you can work with the weights, whatever. But then Bruno asked at the time of day in Italian, and I got really mad at him. So I don't know, it is smart enough to know that he was being sarcastic. But okay, anyway, one fun thing we did have is that in this particular cosmology model, after some hand holding but not telling it the answer, it generated one of the things that was interesting, that was one of the key ideas in the physical paper. So there may be hope for that sort of, everyone knows this sort of hypothesis generation stuff is maybe the most promising avenue right now to replace ourselves, by it being, able to make associations and be creative, even though it's so often wrong when it comes to actual facts. So that's the end of that. And you can do more of the kind of stuff we heard this morning with hyperbolic manifolds, but I will not belabor that. Let's just we just go back to the real summary and stop there. Thank you.
Yeah, thank you. Yeah, unfortunately we're over time, but maybe one question. Yeah, Mr. DC.
F naught equals -1 is what you had in your slide?
Yeah.
In what units?
What units? Let's see.
And I think this is related to Ben's question about like what do you initialize the energy overall? Like there's an
that's-
overall
oh, yeah,
scaling
yeah.
that you can do the whole problem. And so when you say -1, it means something.
Yeah, what I mean is yes. Right. So okay. So the way I parameterize everything in these formulas, we have. Yeah, I understand why you're asking the question. There maybe we pulled out some factor here, but as we parameterized it, the thing that's what we need, what we're doing is that the thing that's raised to a huge power has to be bigger than 1. That's it. And yeah, it's possible that we set some dimensional thing to 1, as we often do in physics, but that's but the principle is that the speed doesn't die, so you take whatever's inside of here and make sure that it's bigger than 1.
Okay, thank you again. And that's it for today. Yeah.